Hello, I welcome you all in the second lecture on the resistance welding processes, and in the last lecture I have talked about the basic principles by which weld joints are developed, and we know that in resistance welding processes the heat used for the development of joint comes from the I square RT heating principle. So, the selection of the welding current, the time for which the welding current is applied, and the pressure which is applied under which the joint is made, these three factors become extremely crucial, because the size of the nugget or size of the nugget which is formed under the resistance spot welding process like projection, seam, spot, etc., we will see that the size of the nugget is governed by primarily the amount of heat being generated. So, the factors that govern the heat generation are these, and here you will see the welding current I is determined by the certain factors like the electrical resistivity of the material. When there is a flow of current I across the sheets to be joined, then the resistance offered by the material for the flow of the current significantly affects the heat being generated. So, electrical resistivity, high electrical resistivity materials offer the more heat as compared to the low resistivity materials. So, if the material resistivity is low, like for the electrical resistivity of the material is low like for the copper or aluminum systems, then we need to set the higher welding current. Similarly, thermal conductivity K of the material also plays a big role in identifying the suitable value of the welding current, because whatever heat is generated at the contact interfaces, that will be dissipated far at a faster rate according to the conductivity of the material. High thermal conductivity materials transfers the heat very rapidly as compared to the low thermal conductivity materials. That is why they require more heat generation for formation of the nugget of the desired size, and so the welding current requirement increases, and thereafter we have the thickness of the sheet being welded. Thickness of the sheet, like thin sheets will be offering the greater resistance for the flow of current as compared to thick sheets. So, thin sheets will require lower welding current as compared to the thick sheets. Apart from the thickness, we have also to consider that how many welds have been made earlier to take care of the how many spots or the joints have been made earlier. Like say if the one joint has been made, the low current may be good enough, but as soon as we start developing another joint, by the shunting effect, current will be flowing through the earlier made nugget, and this will reduce the actual flow of current through the required location, and this will reduce the heat generation, and in turn it will also reduce the size of the nugget. So, the shunting effect also need to be considered when identifying or when selecting the suitable value of the welding current. Thereafter we have the time which is normally measured in terms of say the hertz, like it may be 2 hertz to the 100 hertz for the 50 hertz current. So, time basically we can, if we see this equation, time directly affects the heat being generated during the spot welding process or the resistance welding processes. So, what we have to see that the welding current is allowed to flow through the plates for sufficient period, so that the heat generated forms the weld nugget of the sufficient size, and therefore the parameters, the material parameters like the K thermal conductivity, electrical resistivity, and the thickness of the material, all these play a significant role in selection of the suitable the time for which current should be allowed to flow from the current should be allowed to flow during the welding. Then the pressure ensures the kind of intimacy between the plates being joined. So, if the pressure is less, then it may lead to the arcing between the plates as well as between the electrode and the surfaces of the workpiece. So, there has to be sufficient pressure, but pressure should not be too high, otherwise it will cause the indentation on the surface of the workpiece. So this will act as a stress concentration, because it will be changing the geometry of the plates or the dimensions of the plates in a very localized manner. And another thing, so the factors that govern for the optimum pressure, which is normally kept like 30 to say 70 MPa. 70 MPa is found enough for the mild steel plates, and how the pressure is calculated, like the load is applied divided by the contact area through which the load is transferred through the electrodes onto the surface of the plate. So this one is also governed by the number of material related factors, and which are mainly the mechanical factors for which will be governing the deformation of the material. So these factors are like in mechanical properties, we have yield strength of the material. High yield strength materials require greater application of the load in order to achieve the kind of metallic intimacy which is needed, and the percentage elongation. The high ductility materials will require lesser load or pressure as compared to the low ductility materials, and similarly the thickness of the sheets being welded. So thicker sheets will be require the more load, heavier pressure as compared to the thin sheets, in order to ensure the desired the contact between the workpiece at the frame surfaces or at the interface. Apart from this, the welding current which is to be used, that will also affect the time as well as the pressure to be used. So these are the factors which are to be considered for selection of the pressure as well as the welding time and the welding current. During the process, the current is regulated in a specific manner, especially in case of especially in case of the hardenable steels. Say for example, hardenable metals like medium or high carbon steels or other alloy steels, which under the high rate of the heating and cooling conditions respond to the heat as well as the structural transformation, which in turn affects the mechanical properties of the joint as well as of the sheets. So these must so in these cases, in such cases, the welding current must be regulated properly, or must be changed properly for the welding purpose. And what is that? The welding current value is increased gradually, and it is also reduced gradually after the welding time. So this is called slope up, the rate at which the welding current value is increased from the 0 to the desired set value, and then here it is kept constant for the welding period, and thereafter gradually it is allowed to reduce. So as a function of the time, how the value of the current changes, that is what will be shown, the up and the down, and here what we will see, the welding time period. In this case, up period will be deciding the rate at heating rate. Too high heating rate may also be a problematic, as well as the too high cooling rates can also be problematic. So to like say in case of the so up current value should be adjusted appropriately in order to avoid overheating of the surfaces of the plates, as well as in order to avoid the possibility of the expulsion of the metal from the interface. So, if the current is increased rapidly, then excessive heat generation at the interface can lead to the formation of the molten metal can start coming out of the interface. So, this is expulsion tendency is reduced. Similarly, in the case of the downtime, the temperature, the welding current value is reduced gradually. So, things will be heat generation will be reduced gradually, and this will help to reduce the cooling rate experienced by the portion which was heated during the welding, and a reduced cooling rate actually reduce the solidification rate, and also reduces the cracking tendency of the heat affected zone as well as nugget, and also reduces the residual stresses if at all they are being formed in course of due to the differential heating and cooling during the welding. So, it is important that the up and the down current values are adjusted suitably in order to avoid the issues and the problems related with the resistance welding processes. So, now we will see the three details of the three specific processes like spot welding, seam welding, and the high frequency welding. So, we will be starting with the spot welding, and thereafter we will be going for seam welding and then high frequency welding processes. So, spot welding is mainly used for developing the lap joints and mainly the nuggets are formed randomly here and there in order to achieve the desired strength, like one nugget is formed and another nugget is formed at required so that the required strength can be achieved. In case of the seam welding, the arrangement is slightly different, wherein the spots or the nuggets they are either very close to each other like this, or they start overlapping each other. This overlap may be 10 to 40%, or it may be continuous. When the overlap is more than 50%, then it is kind of continuous seam weld is made. So, this kind of arrangement is used for the air and watertight joints, and this is for the high strength joints, and when the continuous is made, that is for the gas tight joints. In case of the gas tight joints, what we will see that between the there is a continuous nugget formation without. So, when overlap is more than 50% and the nugget is formed continuously, and for this purpose mainly the rollers are used, which will be fed with the desired current, which may be continuous or may be fed intermittently. The resistance, high frequency resistance welding process is another newer development, somewhat newer development, which is mainly used for the high volume production of the for developing the joints between the plates as well as the pipes. So, we will talk about all these three processes using this presentation here. What we will see here, in this case one power supply, the two sheets to be joined are kept in overlapping configuration. Through the electrode, the pressure and the welding current is supplied, and once the welding current is supplied for the sufficient period, nugget is formed after the welding like this. The size of the nugget directly determines the strength load carrying capacity of the joint. It may use the low AC current or the high DC current, but the frequency of the current which is used in this case is normally low, which varies from say 350 to 350 hertz, and for these welding processes normally the value of current is very high, which is in thousands of the ampere. So, This is what I have explained. The control of the upslope and downslope is important. Upslope avoids the overheating and expulsion, and downslope avoids the cracking by lowering the cooling rate tendency. And there are three types of the electrodes which are used for the spot welding process. One is like flat, like this. Another is a truncated cone type, which is like this, and another is dome type. In the dome type, here hemispherical shape dome is there. So, in case of the truncated, the angle between the conical surfaces is of 120 to 40, but this kind of system veers at a faster rate. So, we know the change in the diameter, say initially this is the diameter is this much, then wear will simply result in the increase in the diameter of the electrode tip, which will be coming in contact with the workpiece, and which in turn will lower the current density being fed. Now, current will be fed over this area instead of the smaller area. So, reduction in current density basically will be reducing the size of the nugget, which will be formed due to the in case of wear of the electrode. So, the dome shaped electrodes are used for the heavy load and for whenever the severe heating conditions exist, and the flat tip type of electrode, the entire surface come in contact with the surface of the workpiece. This type of the electrode causes the minimum indentation of the workpiece surface. Then the water electrode, since the heavy current is handled by the electrodes, so and these are mostly made of the copper and copper based alloys in order to have reasonably high temperature strength, and in order to resist the wear, normally the alloys of the different systems like copper, chromium, copper cobalt, copper tungsten, and other mixtures and other alloying elements in the copper are used in order to increase their capability to withstand at the higher temperature, but still it is required that the temperature is temperature of the electrodes is made within the safe temperature limits. That is why mostly the electrodes, despite of being made of the copper, which has very good thermal conductivity, these need to be water cooled, so that the life of the electrode tip, means the electrode life of the electrode can be improved, and unnecessary damage to the electrode can be avoided. Now, it is important, it is very important to see that how the ease of the welding by the spot welding can be assessed and checked, and for this purpose normally there are three parameters: the electrical resistivity, thermal conductivity, and melting point of the metal. These three parameters significantly affect the ease of the welding, and here if we will see that high electrical resistivity, low thermal conductivity, and low melting point is always desirable. So, that given amount of the heat will be melting the metal at the interface at a faster rate. Heat generation, high R means high electrical resistivity, will ensure the much means the higher heat generation for a given current supply. Low conductivity will reduce the heat transfer, heat dissipation to the base metal, and the melting point, low melting point will ensure that the melting takes place at a faster rate, and these all combination of all these three factors in turn will be resulting in higher weldability. And reverse will happen when the value of the K is high, value of resistivity is low, and the melting point is high. So, if we consider the aluminum and copper, which are known to be of the higher thermal conductivity and lower electrical resistivity, that is why they are found to be difficult. That is what we will see from this equation, that the weldability for the spot welding can be checked using this simple formula, wherein electrical resistivity divided by thermal conductivity into the melting point multiplied by 100. This will give us the weldability W in terms of the percentage. So, where electrical resistivity in micro ohms per centimeter and and the thermal conductivity, that is the relative thermal conductivity of the metal with respect to the copper, and melting point in degree centigrade. So, when these thermal and physical properties of the material are used for calculating the ease of welding by this spot welding, then we will be able to know that how much value of the W we are getting, or that is the weldability we are getting. So, the W if the weldability is more than 2, then the weldability is considered to be excellent. If the weldability is between the 0.75 weldability of the W or the weldability of a metal is more than 2.5 and less than 2, then it is considered a good weldability, and if the weldability is less than 0.2, then it is considered as poor weldability. So, here if you will see, for mild steel the W comes out to be of 10, which is considered to be very good weldability by this spot welding, while the W or the weldability for the aluminum comes out to be between 1 and 2. So, here now we will see the application of the spot welding mainly in the field of electronics, electrical contact, aircraft, automobiles, and the home appliances. Now, we will see the seam welding, as I have explained what the seam welding is. Overlapping sheets are gripped between the two rollers of the electrodes, and then current is fed. Current may be continuous or the discontinuous. So, accordingly the nuggets will be formed either continuous or at certain intervals. So, the welding current, as I have said, it may be continuous or it may be intermittent. So, the kind of arrangement which is used here is like the two overlapping plates are kept one over other, and the roller which will be applying pressure as well as feeding the current also. So, when the sheets are rolled between the rollers, the welding is performed. Now, the weld joint will be means this when the sheets will be passed through the rollers, the as per the kind of supply of the welding current, there may be continuous nugget formation or there may be intermittent nugget formation. So, which kind of nugget will be formed, that is what we will see here. The nugget may be formed with a certain kind of overlap like this, or this is one like say this is one cross section of the nugget formation. These are this upper roller, lower roller, and the nugget is being formed, and the nugget is being formed at, with certain kind of the overlap. So, this is the real photograph of the seam welding arrangement. So, here you will see the overlapping of the weld nuggets may be 10 to 50%, overlap approaching 50% is termed as a continuous weld. Overlap 30 to 40 welds are used for the air and water tightness, and gas tightness requires 40 to 50% overlap for the welding purpose. And this is the schematic arrangement showing the tack welding. Tack weld means there is a lot of spacing between the nuggets which are formed, and then lap weld, the nuggets are overlapping with marginal amount, maybe 5%, 10%, and in case of the continuous, now this value can range from the 10 to 50%, and in case of continuous it is more than 50%. You will see that there is a continuous nugget formation. So, this seam welding is mainly used for making the petrol tanks for the automobiles, seam welded tubes, the drums, and other components for the domestic application, and this process is very fast. So, this is very economical for the high volume production to produce a good quality weld. It does, but the limitation is that the equipment is costly, requires maintenance, and maintenance is expensive. Further, the process is limited to the thickness less than 3 mm, because the thicker plates will require much higher amount of the welding current, pressure, and much closer control over the process. Now, I will talk about a little bit the high frequency welding process. High frequency welding process comes in two variants. One is resistance based and another is induction based. In case of the resistance type, the high frequency welding process, actually the contact is there between the components, means the contacts will be supplying the current to both, and then pressure is applied for the welding purpose. So, this high frequency current, this high frequency current basically allowed to pass through the surface. So here this high frequency current basically localizes near the surface wherever we want. It does not flow across the thickness or across the cross section, but the current is allowed whenever high frequency current is it passes through very near the surface layers, and this feature is found very useful in the sense that instead of the flow of current through the entire section or entire thickness, it flows only through the near surface layers, and which ensures that very small volume will be experiencing the flow of current. So, even lesser magnitude of the current is sufficient for generating the required amount of the heat. So, I square RT heating becomes effective because the flow of current is through the very smaller area, and this makes the process effective in the sense that current flows through the very thin layer of the metal to be joined, and once this current flow starts, the heating takes place very quickly, and quick heating over a very small area ensures the softening, and once the material is softened, the two are forced together using suitable pressure. So, this is one approach. In another approach, only the coils are brought close to the surfaces, they are not brought in actual contact, like wherever the joints are to be made, they are the coils with the required type of the current, high frequency current, they are brought in close to the surface wherever joint is to be made. So, again by the induction current, the current is induced very near the surface layers, and then once the current is induced and very localized over a smaller area or near the thin surface layers, that generates the heat by I square RT heating. So, in both the cases the I square RT heating is involved for generating the flow of for generating the heat, but the volume of the material that experiences the flow of heat is very limited. That is why even a smaller magnitude of current is sufficient for the generation of the heat and soften the metal system. So, actually the magnitude of the current which is required in case of the HF current is very low. So, current value is reduced drastically when it is used because high frequency currents will be flowing through the surface layers, not through the entire cross section or entire thickness of the plates being welded. This is what is exploited in the high frequency welding process, and here there is a direct relationship. Normal spot welding, seam welding processes, they use the current of frequency 350 to 350 hertz, but in this case it varies from 1 kilohertz to 1000 kilohertz. It is common to work with 400,000 hertz current for the seam welding process, and whenever the seam welding process is used and the frequency of the current directly affects the depth up to which current will be penetrating to the surface. Like if the current is generated here, then it will be able to penetrate over a very small depth, and this depth varies significantly. This is called current penetration depth, current penetration depth, and this depth is found inversely proportional to the frequency of the current. So, if we see the frequency here 1, like say 10, 100 and 1000, it is the kind of the frequency of the current which is being fed, and in this side if you are getting the depth in mm by which current is able to penetrate. So, here if say this is 0.05 in mm, then here it is like say 1.5 and say 20 depth by which current is able to penetrate to the surface. So, here it comes down directly like this, and here it comes down like this. So, for the different metal systems, this is the kind of the band which is observed. Yeah, goes in like this. So, this for the metals, different metals and the metals in different temperature conditions, we will see that these values may vary like this or like this, but invariably with the increase in thickness, with the increase in frequency of the current, there is a reduction in the depth up to which the current will be able to penetrate. So, like here in case of the high frequency resistance welding, current is fed, heat is generated, and then the pressure is applied, so that the joint is forced or joint is made. In case of the high frequency induction welding system, the coil is passed, so the high frequency current is generated, it is localized near the surface layer, and by heat generation, the surface layers get softened, and with the application of the pressure, these are forced. This is the same thing here, high frequency current is allowed to flow through, and the pressure is applied through the rollers in order to develop the joint. There is another example, these are the rollers which will be forging the things together, and induction coil will be generating the high frequency current in the tubes to be welded. So, this is how we can see, this is for this is another arrangement of the contact type. The earlier one was the induction type arrangement for making the pipes, and this is the kind of contact type. So, the high frequency current is fed to these coils, and the rollers will be forging them together once the edges are softened, and this is how the high frequency current will be localized near the surface layer, and low frequency current will be localized at somewhat at the greater depth as compared to the high frequency. And because of this, since the current is limited over a narrow area, so heat affected zone width is very small, and accordingly the quality of the weld which is made is better as compared to what we have observed in case of the conventional spot welding process. And this is what we can see as a function of the frequency of the current, the depth of the penetration decreases rapidly, and for the different metal system, of course, the decrease is different. That is what we can see here in this diagram. This line corresponds to the iron nickel systems and iron silicon systems, and for the aluminum, the depth of the penetration decrease in depth of penetration is somewhat lesser for aluminum and copper. So, now I will conclude this presentation. In this presentation, I have talked about the resistance welding process, and the three types of resistance welding process: one is spot, another seam, and third high frequency resistance welding process. I begin the lecture or the presentation with the factors that should be considered for selection of the important parameters like welding current and the welding time and the pressure, and thereafter how to calculate the weldability of the metals for the spot welding, and thereafter we have looked into the basic principles related with the seam welding, spot welding, and the high frequency resistance welding process. Thank you for your attention. In the next presentation, I will talk about the solid liquid based processes like brazing and soldering. Thanks for your attention.